Hi, my name is Dr. Beth Phillips from the United States Air Force Academy. I'm presenting Comparing Virtual Reality Interfaces for Teleoperating Robots on behalf of my students, Cadet Rebecca Hetrick and Cadet Nicholas Amerson. Because by the time this video reaches you, Becca and Nick will have commissioned as first lieutenants in the first class of officers in the United States Space Force. So way to go, Space Cadets. Let's get started. So, deft robot manipulation, especially at a distance, can save and improve many lives. Whether repairing the International Space Station from the outside, exploring a defunct nuclear reactor, or providing medicine to patients in quarantine, or providing individuals with motor impairments improved mobility, robots have the ability to go places where humans should not, and both literally and figuratively can extend the reach of their human counterparts. However, even the most advanced robots today struggle with autonomous dexterous manipulation. Roboticist Stephanie Telex at Brown University, one of our collaborators, is often quoted with saying most robots can't pick up most things most of the time. As a result, human teleoperation for robot manipulation and grasping is often employed as a practical alternative because it leverages the expertise and background knowledge of humans to help robots overcome limitations in their autonomy. But we know from a plethora of research that human teleoperation of robots is often really difficult. We know that existing methods and interfaces for teleoperation often place significant cognitive demands on humans, and because of that, they often require humans to translate 3D information about the world into 2D representations and then back to 3D when actually trying to pilot the robot. And in many cases, this requires more than one human operator to control any given robot, which is a problem. Fortunately, renewed interest coupled with the lowered cost of many augmented and virtual reality interfaces have sparked a lot of research that has shown that AR/VR interfaces provide promising solutions for many of the challenges associated with robot teleoperation. Specifically, prior lab studies have shown that VR interfaces for teleoperating robots and manipulation tasks are far more effective and easy to learn for novice operators than keyboard and monitor interfaces that represent the state of the art. Knowing that we have a good initial positive results, we know that it's probably a good idea to continue to explore how VR interfaces can help humans overcome challenges associated with robot teleoperation. For instance, it may be possible that some control paradigms are better for certain types of manipulation tasks than others. Thus, the purpose of this work was to test the efficacy, usability, and cognitive workload associated with using two different virtual reality interfaces to teleoperate a robot to perform a variety of dexterous manipulation tasks. Full system details and open source code for this project can be found on GitHub at the link located here in the presentation and also in the paper. So we're reporting here participants that we were able to collect before in-person data collection was halted due to the spread of COVID-19. So 12 participants were recruited for this study. They were randomly assigned to pilot a Baxter robot, seen here, to complete a variety of manipulation tasks in one of two interface conditions. The first was a trajectory control interface, which is essentially mirrored a click and drag type of movement on a mouse, where when a side button was pushed on the VR controller, the Baxter's corresponding arm would move in the same trajectory as the controller. The second was a positional control interface, which somewhat mirrored waypoint navigation that you see common in many ground robots. When the button was pushed on the controller, the robot recorded the controller's position as a coordinate in 3D space, and the robot's arm would move to that coordinate until a new one was set. Using the two interfaces, all participants completed two gross motor manipulation tasks. The first was pressing a spacebar on a keyboard 5 times, or performing a drumming rudiment, specifically a paradiddle-diddle. So if there's any drummers out there, you recognize the paradiddle-diddle. Then participants performed 2 fine motor manipulation tasks. The first was the YCB cup stacking task, which is standard in much of the robot grasping community, where you stack smaller cups into larger cups. And the last was a pouring task, where participants were asked to pour small beads out of a container and into a wine glass. After each pair of tasks, we asked participants to fill out the NASA TLX, which is a measure of subjective cognitive workload, and the system usability scale. And for each task, we recorded a measure of accuracy, precision, and time to complete across trials. We found that there was no difference between conditions and cognitive workload, but there was a difference between tasks. So participants found the fine motor tasks significantly more cognitively demanding than the gross motor tasks. In addition, to my surprise, participants in the positional control interface were faster and more accurate in completing both gross motor manipulation tasks as well as the cup stacking tasks than in the trajectory control condition. We think that these results have some interesting design implications. First, our findings on workload imply that it might be a good idea to mirror an adaptive automation approach when using these interfaces. More specifically, we may be able to change the nature of the control when tasks or workload are increasingly difficult for operators. For instance, you may be able to change the gain in movement, in mapping movement from VR controller to robot movement when tasks are increasingly hard. Or cognitively demanding. And it seems that for novice users, the positional control was easier to learn and more intuitive than the trajectory control, which was surprising. This is an important finding because many of the places in which robots are envisioned to work collaboratively with humans are places in which humans have a lot of domain expertise but are not robot experts. This type of interface would be helpful because it can leverage the expertise of people while not requiring them to become experts in robot control, essentially extending the benefits of robot manipulation to a wider pool of users. So here's a look at who we are in case you're ever in Colorado and want to look us up. Thanks for the opportunity to present this work. Please check out our paper and feel free to contact us at any time. Thanks again.